Today, everyone, my presentation concludes the lecture series on the use of GRACE data for assessing changes in accumulated water resources on land and below the Earth surface. The implementation of GRACE data in groundwater monitoring is performed in the international GRANDE-U project. As a reminder, GRACE data is openly available and has been processed from gravity measurements into the total water storage index. This index includes total amount of water stored in various continental reservoirs, including groundwater. Based on principle of mass conservation, total water storage changes can be expressed through water balance equation as difference between precipitation and negative components. Separation of the groundwater storage component is carried out by subtracting the other water reservoirs components, soil moisture, snow, and vegetation water content from the total water storage GRACE. Surface water is not considered because under Polish conditions, surface water is predominantly draining in nature. It's an expression of groundwater where the groundwater table intersects the land surface, and therefore surface water storage and groundwater storage are essentially treated as one and the same. Data on the water content in these components are obtained from the GLDAS water cycle model. That's why the calculation of groundwater storage changes can be simplified to the equation shown below. In our research, we found that direct subtraction total water storage GLDAS from total water storage GRACE results in a phase reversal of the simulated groundwater storage compared to the observed groundwater storage. Therefore, we searched for an alternative solution by testing each calculation method using a physical hydrodynamic model. We came to the conclusion that total water storage GLDAS should account for the long-term accumulation of precipitation and evapotranspiration effects in the water zone. Our approach introduced this accumulation into the total water storage GLDAS index. This accumulation depends on the depth to the groundwater level, assuming that as the groundwater level increases, the length of the summation period for total water storage GLDAS extends to include the current and previous months. Next, I will discuss the verification of our algorithm for estimating groundwater storage using a numerical groundwater flow model. The physical models were developed for the catchment of the Solokia and Brock rivers, which are inflowing rivers of the book. Using these models, we estimated the groundwater storage with an independent method. The groundwater flow model was based on the use of software Groundwater Vistas from the ModFlow group. I will begin with the geological conditions as it dictates the structure of the model. The Solokia catchment is composed of carbonate rocks, chalk, which form a fractured aquifer here covered by a thin layer of quaternary deposits. The constructed model is therefore a single-layer model with an unconfined aquifer. The Brock catchment is composed at the surface of quaternary sandy clay deposits in which a porous aquifer has developed. Under these deposits that are separated by a layer of glacial clays, the tertiary sandy deposits and carbonate rocks of the upper Cretaceous, which form a deeper and poorly identified aquifer. The constructed model is therefore a three-layer model. The first layer, quaternary, is an unconfined aquifer. The second layer, tertiary Cretaceous, is a confined aquifer, and the separating layer is represented by a vertically hydraulic conductivity equal 0.01 meter per day. The geological structure is considerably more complex here, which complicates the schematization and may influence the results. This is a schematization of the hydrogeological conditions of in the Solokia and Brock catchments. While the groundwater flow system in the Solokia is relatively simple and single-layered, in the Brock catchment, it is important to note that fluctuations in the groundwater level and those changes in groundwater storage are limited to area where unconfined aquifer occur and are hydraulically connected to the confined aquifer. Research in such a system is therefore a columnar process rather than distributed uniformly across the area. When considering the groundwater flow patterns in catchments with different geological structures, it is important to remember that the presented hydrogeological cross-section are typically drawn with significant vertical exaggeration. This approach simplifies the interpretation and visualization of subsurface geology at the local scale, but it can also unnecessarily complicate the pictures and the regional scale. The diagrams shown above have been prepared without applying any vertical scaling. From this example, we can conclude that the most important factors are type, geological structure of the catchment, and the spatial arrangement of the formations that make up the active groundwater exchange zone. This underscores the considerable potential of statistical model based on machine learning, which, unlike physical models, don't require fully three-dimensional representation. Both models were constructed using a discretization grid with 500 meter resolution. In the first stage, a steady-state model was developed on which calibration was performed by auto-adjusting the hydraulic conductivity with average research value for the 2013-2023 period. The calibrated models were then converted into transient models with a monthly time step. A few words about the boundary conditions and parameters. The catchment boundaries were represented by type 2 no-flow boundary conditions, a type 2 well boundary condition was used to represent groundwater extractions, rivers and their effluents were simulated using a type 3 drain boundary condition. In addition to hydraulic conductivity, the model parameters included research unique for each time step and the specific yield. In the Brock model, the boundary conditions and parameters were defined similarly to those for the Solokia River. However, due to the potential for strong drainage by the Buk River, the southern model boundary was extended all the way to its riverbed. The extent of the Brock catchment in the model is shown in yellow. During calibration, the groundwater watershed between Buk and the Brock developed naturally and closely matched the surface watershed, contradicting the hypothesis of an exceptionally strong influence of the Buk on regional drainage conditions. Only the results for the Brock catchment, the yellow area, were used for water balance analysis. The high hydraulic conductivity values refer to areas outside the catchment within the model domain. Hydraulic conductivity doesn't exceed 32 meters per day. Calibration of the hydraulic conductivity was carried out using the PEST model. The process utilized data from over 300 hydrogeological boreholes in the Solokia catchment and over 100 in the Brock. As can be seen, the calibration results can be considered satisfactory. It is worth noting the significant difference in elevation range between the two catchments, approximately 100 meters for Solokia and around 30 for Brock. There is also notable difference in the absolute elevation of the two areas. In the Brock model, only the first wire representing the quaternary aquifer was subject to calibration, as the tertiary Cretaceous wire lacks any hydrogeological characterization. Calibration error is also affected by the uneven spatial distribution of boreholes, which are concentrated in areas with intensive groundwater extraction. The model results cover the period from January 2013 to December 2023. Input data for estimating research were obtained from the GLDAS model. Absolute values were established based on the total outflow Brock River, using the assumption that the outflow calculated by model drain outflow must not exceed the observed values river outflow at the water station. In the case of the Brock River, it should be noted that the drain outflow estimated using the hydrogeological method occasionally exceeds the minimum river outflow recorded at the water station. Likely causes include high evapotranspiration in the valley, the presence of 10 weirs along the Brock and its tributaries, and unregistered water intakes from the river. The calculated correlation coefficient between the in-situ data from point 1808 located in the center of the Brock catchment and the model results is 0.84. 4.864 located in the southeastern part of the catchment. The correlation coefficient is 0.72. This point is situated near a concrete plant and is influenced by groundwater abstraction. It is important to note that in situ groundwater level measurements are used to estimate the specific yield characteristic for the catchment. These values are determined by successive approximations aiming to match the amplitude of modeled groundwater level fluctuations with those observed at monitoring points. For the Solokia catchment, the specific yield value is 0.01, while for the Brock it is 0.006. These values are lower than the typically specific yield values for aquifer materials. This is due to the fact that the volume of aquifers within the catchment is significantly smaller than the total volume of the soil matrix, which is largely composed of low permeability deposits. Moreover, groundwater storage changes generally occur in unconfined aquifers where water table fluctuations are possible. The volume of the soil matrix meeting these conditions represents the active water storage capacity within the fluctuation zone. In the Solokia catchment, the correlation coefficient between the modeled and observed groundwater level at point located in the northern part of the catchment is 0.83, which is comparable to the results obtained for the Brock catchment. A comparison between the groundwater storage estimated using our formula based on GRACE data and the values calculated from a hydrodynamic model is shown in the slide. The blue line represents the values derived from the model, while the orange line shows the output of our algorithm. The correlation coefficient 0.8. We are currently working on incorporating the spatial variability of research delay into the algorithm. The correlation obtained for the Brock catchment is lower at 0.71. This may be caused by several factors, including a higher contribution of evapotranspiration drainage to the water balance, stronger anthropogenic impacts such as groundwater abstraction, and numerous weirs, as well as a complex, multi-layered, and often heterogeneous geological structure. Another contributing factor may be upward leakage from the deeper confined aquifer within the drainage zone. Another approach used to verify the accuracy of our groundwater storage estimation algorithm was comparison with groundwater storage values calculated using the groundwater level fluctuation method based on monitoring well data and specific yield. The comparison between in situ and groundwater storage GRACE showed very good phase agreement across all groundwater level depth categories. However, with increasing depth to the groundwater table, a time lag effect in the simulated groundwater level compared to observed. At depth to approximately 6-7 meters, the lag is about 1 month, and at depths greater than 8 meters, it increased to 2 months. Additionally, groundwater storage GRACE exhibits smoother variability, lower amplitudes compared to the observed value in monitoring wells. This indicates that the proposed method for estimating groundwater storage is not well suited for simulating groundwater storage in areas where the water table is deep. To improve the configuration of the groundwater storage GRACE simulation model, calibration was performed using data from wells, groundwater storage in situ, and applying random forest machine learning algorithm, as well as Kriging interpolation. As expected, the calibration helped to bring the simulated groundwater storage GRACE values closer to the observed data, with correlation coefficient exceeding 0.8 at all calibration points. A significant improvement in root mean square errors was also achieved following the calibration. The special presentation of seasonal anomalies in groundwater storage GRACE reveals regional patterns. The groundwater storage changes begin in areas with shallow groundwater level and gradually propagate toward areas with deeper groundwater level in river valleys, where the depth to the groundwater level reaches up to 2 meters. Negative groundwater storage values appear earliest starting in April and lasting until September. In areas with groundwater level depths between 2 and 4 meters, the anomalies occur from May to October, and in regions with depths greater than 10 meters from July to December. The phase lag between valley areas and the watershed zones is approximately 3 months. The amplitude of groundwater storage fluctuations shows a tendency related to the hydrodynamic regime. Drainage zones, river valleys, exhibit amplitudes of groundwater storage then are about 1.5 times lower than those in recharge zones. The magnitude of seasonal groundwater storage fluctuation depends significantly on the properties of the aquifer rocks. The delivery of the same amount of water causes a greater rise in the groundwater table in rocks with a low specific yield, indicating an inverse relationship between groundwater level fluctuation amplitude and specific yield, while the relationship between groundwater storage and specific yield is directly proportional. However, seasonal variability of groundwater storage in areas with higher specific yield values is lower. The diagram illustrated this inverse relationship between seasonal groundwater storage variability expressed as the standard deviation and specific yield. For specific yield values around 0.0506, similar average standard deviation are observed. The decline in standard deviation begins at the specific yield 0.07, reaching a maximum reduction of approximately 10% at the highest specific value of 0.16. Regarding the amplitude of seasonal groundwater storage fluctuations, the effect of specific yield manifests as an 18% decrease at the highest specific yield values. Seasonal changes in groundwater storage were also assessed from a spatial perspective within the Bug River Basin, lowland and upland zone were distinguished. The upland zone was further divided into northern and southeastern parts to investigate whether total water storage anomalies observed in the southeastern part are also reflected in groundwater storage. Matrix plots show that the spatial patterns of groundwater storage changes across the three regions are similar, with greater similar between the upland parts. Moreover, monthly groundwater storage changes exhibited opposite directions. Increases in groundwater storage predominated from October to April, while decreases were observed from May to September. The longest periods of negative groundwater storage values lasting 6 to 8 months occurred in 2015, 2018, and 2023 years with predominantly positive groundwater storage values lasting 8 to 9 months included 2017, 2020, and 2021, which corresponded to better conditions. The comparison of annual average total water storage and groundwater storage clearly shows differences in values, spatial distribution, and temporal trends. Total water storage varied from -7 to 10 centimeter, while groundwater storage exhibited a much smaller range from minus 2 centimeter, indicating a significant contribution of shallow storage variability to total water storage fluctuations. The observed special differences emphasize that total water storage is controlled by the precipitation evapotranspiration balance, which exhibits zonal pattern. In contrast, groundwater storage reflects local characteristics locally corresponding to the heterogeneity of water cycle transformations influenced by surface properties and hydrogeological conditions. Temporal differences are also noticeable. Total water storage is dominated by years with negative values, while groundwater storage showed negative values only during 2014, 16, and 2019, 2020. These differences are caused by the high resilience of groundwater reservoirs to precipitation recharge deficits. To explain the temporal variability differences between total water storage and groundwater storage, an analysis was conducted based on time series decomposition. It was found that for both series, the long-term trend and seasonally were the dominant components of temporal variability, but they exhibited distinct characteristics. Total water storage showed a declining trend and high amplitudes seasonally, while groundwater storage exhibited a near zero trend, low amplitude, and seasonal pattern shifted by 1 to 2 months. It can be hypothesized that the lack of groundwater recharge during the summer period doesn't translate into a decrease in groundwater resources. Evapotranspiration drainage affects the reduction of river flows, but doesn't increase groundwater discharge. The observed decline in total water storage alongside stable groundwater storage suggests that groundwater resources are not being depleted, indicating that the book catchment exhibits high resilience to climate change. In summary, our algorithm we developed allows for monitoring groundwater resources changes in any location. Importantly, this can provide valuable information for regional catchment managers. Thank you for your attention.
Thank you, Tatiana. That sounds wonderful. Yeah, especially that the models that separate groundwater storage look very accurate.